Hi, in this short tutorial video I will be going over the RF-DYNAM Pro add-on module and more specifically the natural vibrations input data that's required for running a calculation. This video is going to be part of a series of short tutorial videos where the ultimate goal will be to run a response spectrum analysis or an RSA. Engineers can choose between executing either an RSA or an equivalent lateral force procedure, which is based on the code. Only an RSA can be ran in RFEM, but the benefit of running an RSA is that it works for basically every type of structure, unlike an equivalent lateral force procedure. So when it comes to the dynamic add-on modules in our base program RFEM, we want to first make sure we have our loads and our supports ready to go in our model. One thing I would like to note is natural vibrations is a prerequisite to all other dynamic modules, and this determines what the natural frequencies and mode shapes of the structure are and must be done before an RSA can be run. So first we can go through the loading of the model. Here you see I have my dead load applied to my model as well as my live load and my snow load. So now the first thing we want to do is go ahead and open up the add-on module RF-DYNAM Pro. So I can scroll over here into my project navigator and you can see I have my list of add-on modules. And you can also see the RF-DYNAM Pro module is located under my favorites folder, and that's because you can favorite any module and have it be located under your favorites folder by right-clicking on it and selecting the favorite option. So now I'm just going to double-click the RF-DYNAM Pro add-on module. And now you'll see that this simple dialog box will come up and you will see that all of the other individual add-on modules are here. And you can also see that natural vibrations is automatically checked, and this is because, as I said, it is a prerequisite. So we can first activate our mask combinations, which is needed, and then you'll see that the mask cases and combinations tab will pop up here. And now all we really need to do is just work from left to right through these tabs. So the first tab we want to go through is the mask cases tab. And the first mask case we want to import is the dead load from RFEM. So now that we have our first mask case created, we can type in dead for this mask case. And then once we go down here and check off from force components of, I can select my dead load. And this will automatically be imported in from RFEM into the module. We also want to make sure to uncheck this option from self-weight of structure. And the reason for this is because the self-weight of the structure is already being taken into account back in RFEM. And if we check this option, then the self-weight will be taken into consideration twice. Now there's an option down here options down here to manually define additional masses, but for now I'm going to leave these empty. And now we can take this mask case and make a copy of it, and then we can name it live, and we can import our live load from RFEM into the module. And then all we need to do is make a third copy and call this one snow. This will be our snow mask case. And then we can go down here and make sure the snow load is being imported in from RFEM for this mask case. So now that we have these mask cases imported, we can proceed by combining these cases into mask combinations in the mask combinations tab. So now referring to the ASCE 716, more specifically section 12.7.2, the standard tells us that we need to include 100% of our dead load. And if I go to the code, you can see that right here. And it also states that when it comes to the live load of a structure, if it's used for storage, then we need to include 25% of the live load. And for this particular example, I will assume the structure is used for storage. So I will use 25% of the live load. So if I hop back to RFEM, I will move the dead load over and include 100% of the dead load by keeping this factor 1.0. And then I can move my live load over, and all I need to do is double click on this factor and change it to 0.25 and hit enter. And now we have a factor of 0.25, so we're only including 25% of our live load. Now the code also mentions that for our snow load, if it has a magnitude of over 30 psf, then we need to include at least 20% of our snow load. This example, if I go back to RFEM and I hit OK and go to my snow load, you can see that I have 32 psf applied to the structure, and so now we can move our snow load over and apply a factor of 0.2 to the snow load. So now we can give this mass combination a name, and we can call it dead plus 0.25 live plus 0.2 snow. And now finally we can take a look at our natural vibrations case tab. So the first parameter we should take a look at is the number of lowest eigenvalues to calculate. Right now this parameter by default is set to 4, but for today this is fine. We're just going to leave this as default for this example. And then the scaling of mode shapes is the next parameter we want to take a look at, and you can see that there's a couple of options here. Now right now the default is to just take the square root sum of the squares, and with these couple of options I encourage you to take a look at our help manual for the dynamic module, where you can see a little bit more theory on how the calculation is done for the scaling of the mode shapes. And you can take a look at this manual by going down here and clicking on the help button. And within this manual we can scroll up to page 19, and here's where you'll find more information on the other options for the scaling of the mode shapes, and this will help determine if the other options are better suited for your design project. So back to RFEM, the next section of data to focus on is the calculation parameters. And here we want to choose the mass combination that we just created. When it comes to the acting masses, these are controlled by the acting mass matrix as well. So you should be able to see here by default the diagonal matrix with only the translational degrees of freedom is set. So our masses are only going to act in the global x, y, and z coordinates, which you can see back here in RFEM. And you can see there's other options to include both translational and rotational or torsional degrees of freedom. So with these options you'd be including masses about those axes. So there really are a couple of different options you can choose from here, and for now we will just go with the first default option. There are also multiple options for choosing the method for how the eigenvalues will be solved. We have different calculation types you can see here, and for this example in video we will be utilizing the Langkos solver, which is an iterative method used to determine the lowest eigenvalue and corresponding mode shape of larger models. So basically this solver allows the user to determine a quick convergence, and in contrast the root of the characteristic polynomial method will calculate all of the eigenvalues and corresponding mode shapes, so this method will take a lot longer. And when it comes to deciding which set of mode shapes and solver to use, we can again take a look at the help manual for a better understanding of the theory behind these options, and this will help you decide which options are best suited for your project. So we can take a quick look at these on page 21, and I can zoom in and we can see the different types of eigenvalue solvers here and the theory behind each one. So back to RFEM. With regards to the stiffness modifications, we're going to leave this as no stiffness modification for now, but keep this in mind as I'm going to discuss this in more detail later on in the video in the series. And so now we are done basically with entering all of our necessary input data needed to run a calculation for our natural vibrations case. In the next video I will be running the calculation and explain how to interpret the results. So look out for that video, which will be Dynamics Part 2, Natural Vibrations Results, and I thank you for watching.